So this is where we were at yesterday. So we're dealing with 7.3 trigonometric substitution. Now 7.2 was trigonometric integrals. This is not quite this. This is not the same thing at all. So the motivation that we were trying to establish last time is, how do we find the area of a circle like this? And we did it by writing down what the equation of a circle was, and we saw that we can rewrite this expression in terms of two functions of y. Y is two functions of x. Now this positive square root is the upper semicircle, and the negative square root is the one on the bottom. So those two together make up the whole circle. And we said that we can find the area of the whole circle if we just take the area of the shaded region, which is this integral, but evaluated between 0 and a, and we just multiply that area by 4. And if we can take advantage of symmetry, a lot of times that's helpful because it can make the work on us a little easier. Now, we got a problem here because substitution isn't going to work. And I don't really have any choices for integration by parts. Doesn't even stand a chance at working because the only value for dv, the only thing I can put there is dx. It gets nothing else. U would get everything else. So I wouldn't be making the problem any simpler than it already is. So integration by parts isn't going to work. But what I'm about to do, I just want you to follow along with what happens to the problem if I make a certain assumption, and watch how nice the problem ends up being once we make the right kind of substitution. Now, we can't do a substitution u equals anything involving x, but what we can do is we're going to let x equal a sine of theta. Now, why sine of theta? Don't worry about it right now. I'll explain that in an upcoming slide. But notice that I'm not letting u be an expression of x. I'm taking x and I'm making it an expression involving some angle theta. Now, where is theta coming from? You'll see in a moment. But for now, just take it on faith, however little faith that you've managed to establish yourself in me over the last week and a half or so. And let's see how that substitution makes the problem easier. So if I let x equal a sine of theta, well, I can take that derivative. Dx is a cosine theta d theta. So put everything in their place. Substitute those expressions in, and it looks like that. So there's x squared, a square root of a minus a squared minus x squared. All of this right here is what was dx.
And there's a 4, like an understood 4 in front of the integral, if we were actually
Okay, that's if we were trying to do the whole circle.
Okay.
For now, we're just trying to find, if we can get the area of that upper quadrant, finishing the circle is just by multiplying it by 4. But let's just worry about the integral now. Okay. If I take a sine squared, a sine of theta, if I take this and square it, what do I get? What is a sine theta squared?
A sine squared.
It'd be a squared,
A squared.
sine squared. Because this is a product, this is not a sum, so you don't have to do FOIL there. Just distribute the power between those two factors. So now, it looks like that. So these notes I've already written out in advance, and I've tried to, whatever I have changed on the next line is what you see in red. Okay? That's not always 100% the case, but I've tried to make it as visually easy to follow as possible. Now, what does this a squared and this a squared sine squared have in common? A squared. So factor it out. right? If I pull the a squared out right here, there's still a 1 there holding its place. That's where this 1 comes from. Minus this sine squared. That's times a cosine of theta. Here's your trigonometry. Do you remember what 1 minus sine squared was? It's cosine squared. So now this becomes, I think if I hit the next slide, it's going to switch it to the next screen. So when it's okay, when you've written this and it's okay for me to go to the next slide, let me know. Are y'all good? Okay. I had a slow writer in my calculus class, so I'm just checking. So that 1 minus sine squared becomes cosine squared. Now, what is that square root going to do?
You can get rid of if you take the pairs out.
It's just going to leave me with a cosine theta, right? So that square root becomes a cosine theta. But I already have an a cosine theta here. So this is going to become what? A squared cosine squared d theta. What is a squared? Is a constant, right? Couldn't you pull it out of the integral? Sure. And now don't I have cosine to an even power? Now it's a trigonometric integral from the last section. And I can finish it like that. Well, both sine and cosine have even power here, so I would use a half angle identity. That the trigonometric integrals, you only pull off a factor of sine and cosine when the power of that trigonometric function is odd. If both of them are even, use the half angle identities to knock that power down. So this a squared, nothing happened to it. I just brought it down. I haven't even pulled it out of the integral yet. That's going to happen. Just give it time. The cosine squared, this is the half angle identity for it. 1/2 times 1 plus cosine 2 theta. Well, or I could just integrate it like it is. If you let u equal 2 theta, you can integrate this term by term now. The a squared over 2, if you want to pull it out of the integral and simplify that, you can. I mean, this a squared over 2, that's what happened. It came out of the integral. So, but notice that I'm integrating with respect to theta now. It's not x anymore. So a squared over 2 has been pulled out of the integral. The integral of, the antiderivative of 1 is theta. The integral of cosine of 2 theta, you could let u be 1, u equal 2 theta in this case, but it ends up being 1/2 sine of 2 theta. If you question that, take its derivative and verify it on your own time. But this line right here, once you integrate it, becomes that. We are not done. Because the original problem was in x, not in theta. I need to get back an expression involving x. Okay, we can do that. Okay. This is just the double angle formula for sine. Because there's a reason why I want sine of theta, cosine of theta, and it's what you're about to see when I draw the triangle. So the only reason I used this was because I had sine of 2 theta here. I wanted to get an expression involving ratios of just theta. So I used the double angle formula to get that line. Now that 1/2 and the 2 cancel each other. Oops. Okay. Now, we're not done with the problem yet. We're taking a break to try and figure out what theta is and how to fill out this triangle. Remember from when we started working the problem, we let x equal a sine of theta. Well, if I divide both sides by a, won't I get, won't I get sine of theta equal x over a? How do we define sine? It's opposite over hypotenuse, right? So if I've got this triangle, this right triangle, and this is theta, if sine of theta is equal to x over a, then this side has to be x, this side has to be a. And I can use the Pythagorean theorem to figure out what the other side should be. So that will look like this. So now that I've got x and a in the right place, I can use the Pythagorean theorem to get that missing leg. And look what that missing leg is. It's going to look familiar. Where have you seen this before? That's what we were taking the integral of. It was in the original problem. That's not by accident. So theta is equal to the inverse sine of x over a. Now we've got to remember that in order to apply inverse sine, you're in quadrant 1 or quadrant 4. Those are the only 2 quadrants that the inverse sine is defined over. For inverse cosine, it's quadrants 1 and 3. For inverse tangent, it's 1 and 4 as well. But you'll see the right substitutions we need in a moment. So now that I have my triangle filled out, I can go through and identify what all of these quantities are. I know what theta is. It's right here. It's inverse sine of x over a. I know what sine of theta is, because now that I have my triangle, sine of theta is x over a, so I can put that in for right here. Cosine of theta is adjacent over hypotenuse. So I'm going to put square root of a squared minus x squared divided by a. And it's going to look like that. So there's theta plus, okay, the 1/2 and the 2 cancel each other, but this is sine of theta, cosine of theta. And then I have that plus the constant, because it was an indefinite integral. But now it's an expression involving x now. And notice that I didn't have to take any antiderivatives of inverse trig functions. I was able to substitute over into trig functions first, integrate, and then substitute back using what the triangle said the ratios should be. So it looks like a complicated answer, but I'll guarantee you, if you differentiate this, you're going to end up with square root of a squared minus x squared. And I would challenge you to try that on your own sometime and verify if that is what you get. Is there any part of this that you'd like me to go over again? The only part I really haven't fleshed out is how on earth did I know to make x equal a sine of theta from the start of the problem? That's what allowed all of this to happen. But here is what we're going to be looking for. Oh, here, on this line, I just ended up distributing the a squared to these 2 terms, because notice there's an a squared right here. When I multiply this out, this a squared will cancel with the a squared on the bottom right here, and I'll just end up with this expression. But if you would have left it at that top line, That's perfectly fine.
I'm kind of confused about the whole x over a. How you managed to get that.
Okay, the x over a came from, we assumed this right from the beginning. X equals a sine of theta. If we just divide both sides by a, that'll tell me what sine of theta should be in terms of x. That's where this line came from.
Okay.
You said all you did for the last line was just distribute a squared.
Yeah, let me get rid of that box, because as soon as I flip the page, I can't undo anything
But
anymore.
yeah, done the whole equation over a. I figured divided the whole equation by a.
Okay. Yeah, if you take this and you distribute it to both of these terms, you're going to have an a squared over 2 sine, inverse sine of x over a, which is what you see right here. But when I take this a squared over 2 times this second fraction, I still have the over 2, but this a squared will cancel with the a squared you see here on the bottom. But this first line is perfectly fine as if you want to stop there.
I understand how we got to this point, but if I were to see that problem, I would have no idea. I would have never thought to do all of these things to get here in the first place.
Which is why we have more examples to do. So the idea, there are 3 substitutions, and we have to know which substitution to use. In the first problem, a sine theta was the right one to use. There's going to be one for tangent, and there's going to be one for secant. And the way you identify it is you're looking for the square root, and the square root needs to have either a difference or sum of squares. Like in this case, we have a difference of a squared minus x squared. If it is a constant minus the expression involving x squared, that is where you let x equal a sine of theta. What is a? Sort of depends on the problem. If this number right here would have been 16 minus x squared, a is equal to 4. And I would let x be 4 sine of theta. If this is 7 minus x squared, then a is going to be square root of 7 for that problem. And I would let x equal square root of 7 times sine of theta. But this is the substitution you use, and this is the identity you will need in the course of that problem. Because remember, we substituted 1 minus sine squared of theta for cosine squared. That allowed us to get rid of the radical in the problem. It's that radical that's causing the issue. If we can get rid of it, we can end up with something that we've worked before, a trigonometric integral, maybe from section 7.2, maybe we end up with something that needs integration by parts. We don't know until we get our hands dirty and we work the problem. But if it is constant minus expression involving x squared, that is where you use a sine of theta. If it is, oh, and notice what I've got written in red right there. For theta equal negative pi over 2 to pi over 2. Remember, this is quadrants 4 and quadrants 1. That's where inverse sine is defined. If instead of a squared minus x squared, it's a squared plus x squared, you're not going to use sine, you're going to use tangent. And you're going to use the Pythagorean identity involving tangent and secant to get there. Because you notice, look, right here you've got a constant plus some expression involving theta squared. And if you make the substitution, that's exactly what you're going to have. A constant plus some expression involving theta squared. So you'll be able to use tangent, and once you make the substitution with secant squared, you're going to kill off that radical completely. And once it's gone, the problem is easier now. The only case I have left off is what happens if it's x squared minus a squared. Notice x squared plus a squared is the same as the second case. They're both positive. So you treat it, it's exactly the same. But if it's x squared minus a squared, you're going to use secant instead of sine or tangent. Oh, and that's supposed to... There's supposed to be a bar here. And again, notice that the inverse tangent is defined from negative pi over 2 to pi over 2, not including the endpoints. Because remember, inverse tangent is undefined at pi over 2, and it is undefined at negative pi over 2. But the inverse tangent is defined for all values between those two. And inverse secant is defined from 0 to pi over 2 or pi to 3 pi over 2. This is quadrants 1 and quadrants 3. So this is the substitution you would use. This is the identity you would use to cancel the radical in the problem. So it is going, you're going to notice that all these problems that we're working, the square root is going to be the sort of the target in our, that we're trying to get rid of first. Once the square root is gone, I should be left with something I can handle. Can I switch, or you'll still write? If I ever switch and you hadn't finished, if you just want to catch me after class, I can flip back to that slide and let you see it. Okay. For definite integrals, so if you had limits on that integral, it's a good idea to change the limits of integration. If you change the limits of integration, you don't have to draw the triangle and go back in terms of x. You can just evaluate it with those correct values for the limits in terms of the angle measure. But if you have an indefinite integral, like we had in the last problem, you have no choice. You have to draw the triangle and rewrite the answer you got in terms of, your answer would be in terms of theta. You need to write your answer in terms of the original variable you started out with, and the triangle will give you that. Okay. I think it's time to work a problem that has a number in it. Don't y'all think? So I see that I have a definite integral here. I am going to be changing those limits of integration. Now, I see that I have a square root in the problem, and it's not just a square root. It's the fact that under the square root, I have a square minus a square. That is what I'm looking for. If you don't have square minus a square or square plus a square, then you're not going to be able to use this trigonometric substitution. You can try substituting, let u equals 16 minus x squared. But what happens? If u is equal to 16 minus x squared, when you take the derivative of that, what's going to happen to that power? On the x, what's going to happen to the x squared? It's going to become 2x, right? The power is going to go down, right? The numerator is x cubed. It's higher than what your substitution would be. So derivative is not, you're not going to be able to take a derivative and get the expression in the numerator from it. So you can try substitution here, and it's worth trying it to see what kind of difficulties you have in finishing the problem. So here, because I see square root of square minus square, or constant minus an expression involving x squared, then tell me, what should I let x be? What is a in this case? 4. So I should let x be 4 sine of theta. Yes. So 4 sine of theta. I know I'm going to need dx. I see it in the problem. So I'm going to go ahead and differentiate that and get 4 cosine of theta, d theta. And this right here, I may need this, but that's going to come at the end of the problem. So if this right here is not, I'm not going to need it right now. It's going to come back up later. I got a lot of steps to get through before I ever come back to that. Okay. Now, I'm changing my limits of integration. So rather than going from 0 to 2 pi to 2 square root of 3, I'm going to take this expression right here. Oh, no, I'm sorry. This is where I use this. Because if x is 2 square root of 3, if I plug that in here, I'm going to end up with 2 square root of 3 over 4, which is inverse sine of square root of 3 over 2. This is where, if you bring your unit circle and just keep it with you, you can use it. Because remember, inverse sine, you need an angle in quadrants 1 or 4 between negative pi over 2 and pi over 2 that has a cosine, that has a sine of square root of 3 over 2. And that's pi over 3. So my upper limit of my integral in terms of theta is now going to be pi over 3. The lower limit, if x is equal to 0, well, 0 over 4 is just 0. Inverse sine of 0 is 0. So my limits, instead of 0 to 2 square root of 3, it's going to be 0 to pi over 3. And everywhere I see x or dx, I am substituting their appropriate values into the right places. So here is x cubed, 16 minus x squared, and all of this right here is dx. So there's going to be a lot of simplifying on the next step. 4 cubed, that's where the 64 came from. Technically, there's another 4 right here. So if you wanted to put 256 right here and leave and remove this 4, you can do that. But there's a reason I left it like this. And you'll see in a step in a moment. But my numerator is now 64 sine cubed. Look at my denominator in the square root. Notice that there's a 16 in common. How about I factor the 16 out? Just like I did the a squared in the other problem. So I'm going to factor 16 out of that denominator. And it will look like, well, okay, I ended up combining that 64 and the 4 in this next step. I didn't think I did that, but I did apparently. Does anybody need me to flip back to the previous screen? Did you not finish? Okay, there's still... Okay, let me get rid of that because I don't want it there permanently. Okay. I have done no calculus at this point. Everything you see is either algebra or trigonometry or arithmetic. Good? Okay. So the 16 got factored out of that denominator, and I went ahead and broke it apart because it is true that if you have this square root of xy, This is equal to the square root of x times the square root of y. Radicals do break up like this. And that's what I did with that 16 and that square root of 1 minus x squared. That wasn't necessary. It's just how I happen to have written this problem.
We're gonna know that at 16 in parentheses.
But you're going to be taking the square root of it in the next step anyway. So, tell me, what is 1 minus sine squared again? It's cosine squared, but what is the square root of cosine squared?
Cosine.
It's cosine. So, this square root that you see is really just cosine. And won't it cancel the cosine in the numerator? Yep.
Oh,
From the dx, it was written off to the side. I just pulled everything into the numerator of the expression.
So 1 minus sine squared is cosine squared?
Yes. And the square root of that is going to give you cosine. Now, what is the square root of 16? 4. So it's going to knock that 256 back down to 64. That's why I thought I didn't combine them, because I figured that 16 was just going to cancel that 4 that was written off to the side anyway. But apparently,
So you would distribute the dx
distribute what?
well, I mean, the 4 cosine theta d theta, that's just it.
4 cosine theta d theta.
But
You say like if you would have distributed it.
64 sine d theta times 4 cosine theta d theta. But what you're saying is you wouldn't have, you still got the 64, right?
Right, because there would have been a 4 cosine theta off to the side, and this 4 would have canceled this square root of 16, and that 64 would never have changed. But it's just how you've written it, and I thought I did it one way, and apparently this is an example of there are multiple ways of writing the correct answer. So what does the next step show? Well, the square root of 16 has knocked that 256 back down to 64, and I pulled it out of the integral. Because there are no more constants in the problem, I might as well pull that 64 out now and be done with it. That square root of 1 minus sine squared just becomes cosine squared, and in the very next problem, it's going to cancel that cosine. So what am I going to be left with after that happens? I'm going to be left with an odd power of sine. I'm going to pull off one factor of sine because it is a trigonometric integral now. Rewrite the rest in terms of cosine, and you can see now we've just segued into section 7.2 again. So I've said a lot of steps, but let's look at that written out. So there goes the cosine, it's gone. Here is a factor of sine broken apart.
So how do both of the cosines disappear?
There's only one cosine.
I thought you had a cosine squared at the bottom.
But it's square root. It's square root of cosine squared.
Oh.
So really there's only one cosine in the bottom.
And then they can Great,
Look, it got picked up on audio. No, you're probably far enough away. I'm the one that's got to watch my language.
Dang it. I was so proud of myself.
But that's what I want to make certain is that y'all are. If I got to drag you behind me, I will do that. But what I don't want is to be talking and then look behind and y'all aren't there at all. Y'all should be following along at some point. If there's a part of this going like, okay, I don't remember how we got this step, rework the problem. Start over. Okay? Now, you talk me through it. Why did I break off a factor of sine? What am I going to do from this step?
Make it in terms of cosine.
Take the rest of the factors of sine and put them in terms of cosine. So 1 minus cosine squared. That's the next step. Now, once I substitute that in, what am I going to let u be? It's what you change the expression to. Let u be cosine of theta. Du is negative sine theta d theta. So you're about to see that 64 on the next step is going to become negative 64 because I'm going to take this negative and pull it all the way out. And this sine theta d theta is going to become du. So now it looks like this. And notice the negative on the 64. And now look what I've got. It's a polynomial in terms of u now. I do want to take a moment to mention, notice I did not write any limits of integration. Because as soon as I go from theta to u, it's no longer 0 to pi over 3. I could, if I wanted to, change the limits from theta to u. I'm not going to do that here. I end up substituting back in what u stood for. So I'm going to keep the limits for theta, but I'm not writing them here because to put 0 to pi over 3 in terms of u is wrong. Okay, see, I actually went back and I made a note of that on here. That's why I've got those little blue stars there. Blue stars there to indicate that I did not forget to put the limits. The limits are there. I'm just not going to use limits in terms of u. I'm going to use 0 to pi over 3, but I can't put those limits until I get back into theta. So there's my integration of that polynomial in terms of u. And now I know what u is. U is cosine of theta, so this is going to be cosine of theta minus cosine cubed of theta over 3. Evaluated between 0 and pi over 3. As soon as I substitute back in theta, the limits come back in. And it looks like that. And I can use my unit circle to go, because pi over 3 is on the unit circle. Cosine of pi over 3 is what? Square root of 3 over 2? Is that right? I think that's right. Square root of 3. No, it's the other way around. It's 1/2, right? Okay. See, I don't memorize them. I have to draw it. I draw it in my head. But this is why I want y'all to get accustomed to use. Focus on learning the calculus part of it. Offload your cognitive resources for trig onto the unit circle and onto the trig identity. So if I plug those values in, I get this. This is the expression evaluated at the upper limit minus the expression evaluated at the lower limit. And the rest is just arithmetic. You should get 40 over 3 as the answer to this. Now, tomorrow is the last day of this, class period of this week. I am picking up that worksheet tomorrow. So, if you're not here tomorrow, I expect it in my email by the end of the day. If I don't have it by tomorrow, I'm not accepting it. So, in addition, what I would like you to practice, try this problem. We're going to work this one tomorrow, but try that one, where it's x squared plus 7. You're going to need you're not going to use sine in this problem, you're going to use a different one. But see if you can't work it and see how far you get. You might finish the problem and you won't need my help. That's great. That's just a signal that you've got the right idea. But if you get stuck, I want to know. I would like to know where you get stuck. Because if we can fix it, we can help avoid that in the future. So don't just say to yourself, oh, I'm just going to wait till class and he's going to work it for me. No, you work that problem before class tomorrow. Okay? All right. That's